Welcome back to the Physics Bible. We're going to look at the electricity section, CP9 of the Edexcel Physics GCSE. This is part 2. Don't forget, you could do this. Okay, first question is sketch a graph for a resistor, a filament lamp and a diode. You have to know this. The resistor, I'm going to use the red line. The resistor is what we call an ohmic conductor. It means that its resistance stays the same. And on a current voltage graph, that means that we get a straight line through the origin. So that's our resistor. It means, because it's a straight line, it means the resistance doesn't change. And for a resistor, that's what we want from it. A filament lamp, I remember this because filament begins with F. We're going to use a green line for this. And the filament lamp is actually going to be symmetrical, but it's got a curve on it as well. Now we've got to make sure that we don't curve it all the way around, like flick it up. We don't want to do that, or flick it down. But we do want to show that it changes resistance. Here, the resistance is quite low. So for a small voltage, you can see the current's going up quite steeply. But as we increase the voltage, the current's going up, but it's kind of trailing off, it's starting to curve off. This is because when the filament's hot, there's more resistance. And so even though we're trying to put more and more push into it with more and more potential difference, we're not quite getting the same current out again. It's going up, but it's not going up as quickly as it was going up there. I remember the shape because you can see there that there is an F shape. For filament bulb, a diode, I'm going to use a blue line for that one. So a diode, if this is the negative and this is the positive, in the negative direction, a diode doesn't let current flow in the negative direction. So that stays at pretty much 0. But when we get into the positive section, the current doesn't go up straight away. It takes a little push to activate the diode, but once it's activated, the current shoots up. This happens at around about 0.6 volts. Around that. So once you've reached that level, then the current just rushes right up. That steep line means that the diode has a very small resistance once you've reached that activation voltage. Here's a graph of a thermistor. Describe an experiment that would allow you to obtain this graph. So I'd like you to think about what we could do as scientists to get this graph, to recreate it. And to do that, we need to look at the axes, temperature and resistance. We're going to have to be able to change the temperature of a thermistor and measure the resistance. So I've got a blank page here. I'm going to leave that there for a second. I'd like you to come up with a circuit diagram and in bullet points what you would do to get the results, to get this graph. Have a go. Okay, so on a very basic level, we're going to need the current. So we'll use an ammeter. We're going to need the thermistor, which has a symbol like that. It's like a hockey stick across a resistor. And we're also going to need a voltmeter. Now think about what this gives us. We've got a power source, which is good. We've got a thermistor, and we've got an ammeter and a voltmeter that take the readings of the voltage and current. If the thermistor is the only thing in this circuit, then the voltage is always going to be whatever the voltage is there. So what you might find is that another resistor is added in, even a variable resistor. Another component is in that circuit. Now, if it was variable, you would change it just so that the amount of current wasn't too high to be dangerous. But in general, we would just put a component in there to keep the current low enough so that the experiment doesn't become dangerous. Once we've got this set up, if we go back to our graph, what we actually need to do is vary the temperature. We want to change the temperature and see what happens to the resistance. To get the resistance, we need to know the voltage, which we've got because we've got a voltmeter, and we need to know the current, which we've got because we've got an ammeter. So the thing we have to do is change the temperature. The way to do this is to use a water bath. A water bath allows you to change the temperature of water, and so what you could do is you could set it at 10 degrees, put the thermistor in the water. You might be thinking electricity and water don't mix, but at these voltages it's not dangerous, and obviously we're not going to be in the water ourselves either. As long as we use the right cables and the right type of thermistor, then there shouldn't be any problems with the circuit. We should be able to put the thermistor into water without there being any dangerous effects. So I use a water bath, set the temperature, say 10 degrees, record the voltage, record the current. The reason we do this is because it will allow us to calculate R. Oh, wait a minute, we've got the temperature and we've now able to calculate R. Change the temperature and calculate R so we can get results. The only thing we've got to do is make sure that in our description is we say that we are going to change the temperature to a new one, say 20 degrees, and then repeat the measurements. So you would take V and I and then change to 30 degrees, etc. And let's do that up. Let's do it up to 90 degrees C. We don't want to boil the water. So by obtaining the current and the voltage for each temperature, and we're increasing it by 10 degrees at a time, then we'll be able to plot what the resistance is and then plot a graph. And for a thermistor, we find that the resistance goes down as the temperature goes up. Okay, in this circuit we've got another ammeter and a voltmeter, but this time we've got what's called an LDR, or a light dependent resistor. Explain what will happen to the voltage and the current if a light is shone onto the LDR and then turned off so that it's dark. We need to know what an LDR does when there's light or when there's not light. When it's bright, the resistance is low. It's a bit like the thermistor, but instead of light, it's temperature. So as the temperature gets higher, the resistance goes down. For an LDR, as the light intensity gets more, then the resistance gets lower. And when dark, R is high. So what's going to happen if the light is turned up when it's turned off and on? So when it's turned on, the resistance is going to be low. If there's a low resistance, then we expect to get a high current. When the light is turned off, the resistance of the LDR is going to be high. So this resistor here, it becomes a high number. And because we've only got one battery and there's no other components, for the same voltage, now that we've got a high resistance, it's actually going to cause a low current. So it will cause the current to go down. Now a bulb is put in the circuit also. Explain what will happen to the bulb if the light is shone and turned off again. Okay, let's add that bulb in. So let's think about the effect that it'll have on that bulb. When we shine the light, the current will be high. That'll be the same even if the bulb's in there. If we shine the light, the resistance of this will go down, so the total resistance in the circuit will still go down. There will be less resistance and the current will go up. So when the light is on, the bulb will actually get brighter because there'll be less resistance, and so more current will flow, and if more current flows, that means there's more energy going to the bulb. With the light off, then it's going to be dark, the resistance of this is going to be high, and so the current in the circuit is going to go down. If the current goes down, the bulb's going to get dimmer. These can be used in lots of situations. The thermistor, the light dependent resistor are both examples of components that can be used to monitor an environment. So for example, you may have a thermistor in your thermostat at home. The thermistor will detect when it's a certain temperature. Now it obviously doesn't detect it hasn't got a conscience, but its resistance will change. As it gets hotter, its resistance will go down, and when the circuit detects that the current has got too high, it'll know that you've reached the right temperature. You can also have a thermistor in a kettle, so the kettle knows that when it gets to a certain temperature, the resistance of this will be at a certain point, and then it'll switch the circuit off. Can you think of a use for an LDR? LDRs are going to be used anywhere where you want a change in light to have an effect on something. So you might have a light dependent resistor on a solar powered light outside. When it's bright, the resistance is low. At night time the resistance is high, it'll cause the current to go down. You'll have a separate circuit that would pick up that change, and it will then turn a separate light on. So we're using something that changes to monitor the outside environment, and then we use the changes to the current in that circuit to have an effect on something else. Okay, in the next couple of pages, what I recommend you do is pause the video, have a read through the questions, and have a go at the maths. I'm not going to spend too long kind of explaining these. It's more of a matter of, can we rearrange the equation and can we remember to change the units? Let's read through this quickly. Electricity creates heat energy as it passes through components. Sometimes this is wanted, for example an electric heater or a hairdryer. Sometimes it isn't. For example, a TV can get warm. We say that work is being done against resistance. So the electricity is doing work against the resistance, and the energy is being transferred by heating. The energy is usually dissipated to the surroundings. Now that word dissipated we need to know. It means to spread out to the surroundings. In other words, wasted. Now thick wires have less resistance than thin wires. Explain why the national grid transfers electricity using thick cables. So why would the national grid use thick cables? Have a think, check back. Okay. If they've got less resistance, then that means that there will be less heat loss as the energy passes through. This energy in the national grid, we don't want there to be heat loss, so it would be wasted. Work would be done against the resistor and energy would be transferred by heating. It would get hot. Less resistance means less heat energy created, which means the system would be more efficient. So thick wires means less resistance means less heat energy created, which means that the whole system is more efficient. We've got less wasted energy because less energy will be, and this is where we use our word, less energy will be dissipated. We don't want to dissipate our energy in the national grid. We want to keep it in the national grid. How much energy is transferred when a 12 volt battery powers a fan with 0.3 amps for 5 minutes? This is coming back to the energy equation, ITV. Remember it because of the TV channel. Energy is ITV. I is current, T is time, V is voltage. What have we been given? We've got voltage, we've got current, and we've got time. And what we have to find is energy. So do we have I? Yep. Do we have T? Yep. Do we have V? Yes. Now there's one thing we've got to do before we just put these numbers in, and that's the time. Our time must be in seconds when we use the energy equation. So current is 0.3, I, T, and V. So the total energy that's being transferred is 0.3 divided by 300 which gives us a final answer of 1080 joules. If the current in the lamp is 0.4 amps when connected to a 230 volt power supply, how long will it take to transfer 2000 joules? Pause the video, have a go yourself. Okay, we've been given 0.4, that's a current. We know that V is 230 volts. And we've been given E, it's 2000 joules. So what don't we have? Well, it's asking how long will it take? Which means we have to find T. How long will it take? So we need to rearrange this equation. To rearrange something where we've got 3 letters on the right hand side, we just do exactly the same as we would for 3, an equation that looked like that, where we've just got 3 symbols. The difference is the 2 that you move to the bottom, the one that you would move to the bottom normally, we're going to have to move both of them. So in this case, to leave T on its own, we're going to move I and V, and they're going to be moved underneath the E. Just to see if you've got the hang of it, why don't we write I equals? What would I equal? So if we had to work out the current, rearrange the equation to get I equals. Well, the I would stay where it is. We'd have to move the T and the V, so it would be E divided by the T and the V. What about if we wanted V on its own? For that, we'd have to move the I and the T. That would go underneath the E, so we'd get V equals E divided by I times T. Let's put the numbers into this. We've got the energy. Let's do this down here. The energy is 2000. We've got the current, 0.4, and we've got the voltage, 230. Okay. When putting this into the calculator, I always recommend doing something like this first. So 0.4 multiplied by 230 gives us 92. And now that it's in that form, we can't make a mistake. We know that that's that answer. We'll just do 2000 divided by 92. We'll round that up to 22. So final answer, time 22 seconds, or to be more exact, 21.7 seconds. This next section we're going to be using quite a few different equations. It's linking charge, energy, current and time, and power. So that we don't get confused, we need to recognise what is each symbol. So, you know, what's Q, for example, or what's R, or what's T, and we also need to know what it's measured in, what are the units. So, pause the video, see if you can figure out how to fill in the table, and then we'll go through that in a second. Okay, so we've got the symbols there. The one that people tend to get tripped up on is charge. Charge has the symbol Q. The letter C is actually what it's measured in. So for example, 20C, that means 20 coulombs. So charge is measured in something called a coulomb. Again, that's a French word. Current is measured in amps. Potential difference measured in volts. Time needs to be in seconds. Power is measured in watts. And resistance is measured in ohms. The current in a lamp is 0.6 amps. How much charge flows in 1 minute? For all of these, I would pause the video now and just have a go at each one, and then I'm going to go through it very quickly. Here, we've been given the current, I is 0.6. The charge, we don't know, it says how much charge is flowing. The time, let's not get tripped up, 1 minute is 60 seconds. So Q equals IT, that's one of our equations. 0.6 times 60, which gives us 36 coulombs. That could be 3 marks in an exam. So how could you miss out those 3 marks? Well, if you just put it straight in a calculator without writing down your working out and you got the wrong answer, you'd be throwing away the working out mark. If you write the answer but forget to put the unit, that might cost you a mark as well. So make sure you show your working out and make sure you put your unit on the end of the answer. If the current changes to 0.3, how long will it take to deliver 36 coulombs of charge? How long will it take? Well, in this case we need T. And we need to rearrange it. So T equals, we're going to keep the T, we're going to have to move the I underneath the Q. The current is 0.3 and the charge is 36. So 36 divided by 0.3 gives us 120 seconds. we've got a 1.5 volt lamp transforms 600 joules of energy. How much charge? Right, this is not the same as this because now we're talking about energy. So we've got E, 600, we've got V, 1.5, and it's asking us to work out how much charge Q. Which equation involves energy, charge and voltage? It's this one. The charge is what we want, so that stays where it is. The V has to go under the Q. Sorry, the V has to go under the E. Energy 600, voltage is 1.5, and that gives us a final answer. How much charge has passed through it? 600 divided by 1.5, 400, and remember the units, Coulomb. How much energy does an 800 watt microwave transfer in 1 minute? So what letter does that represent? 800 watts. Hopefully you said power. The watt is the unit of power. So we know that we've got P. We've also got the time, 1 minute. Again, not going to fall for that one. 60 seconds. How much energy? E is what we need. So we've got power, time, and we need energy. Which one of these fits into that? The power equation. We need E, so we're going to have to move the T and it will go up beside the P. So E equals P times T, so the total energy is 800 times 60, which is 48 with 3 zeros. 48,000 joules. We can write that also as 48 kilojoules, because kilo means thousand. So 48,000 joules or 48 kilojoules. What's the current in a 3 kilowatt kettle at 230 volts? So we need current, that's I. A 3 kilowatt kettle, that means we've been given P. Now I'm not going to write 3 because it's 3 kilowatts. So what am I going to write for the power? 3,000. Make sure it's in watts. And the voltage is 230. Now we've got P, we've got V, we need I. We're going to use the PIV equation. To rearrange, the V is going to go underneath the P. So I equals P over V. So I equals 3,000 is the P divided by V, which is 230. Put that in the calculator. And we get an answer of 13 amps, which funnily enough is the maximum current that you'll get in a household. That's the biggest fuse that you'll get in a house. An electrical cable has a resistance of 900 ohms with a current of 0.3 amps. What is the power of the heat dissipated? Right, it's just another calculation question. Even if you don't understand what's going on, if you can circle those numbers, if you can pull out the bits of an equation that you need, you should be able to put the numbers in. So we've got R, we've got I, 0.3, and we need the power. This time I don't have the power. Looking at our equation, we're going to have to use this one, P equals I squared R, because we've got I, we've got R, but we need P. None of these other ones fit. So I squared R, which means P equals I is 0.3 and R is 900. Put that in the calculator. Oh, I nearly did what lots of students do. I nearly forgot to put the square sign there. Very common error that. So power is 0.3 squared times 900. Because of bid mass, it will do the square function first, which is what we want it to do, and then it'll times it by 900. So we get a power of 81 watts. If the current is increased to 6 amps, calculate the power of the heat dissipated. Give your answer in kilowatts. So it's the same situation, but this time the current is going to be increased all the way up to 6 amps. Can you make a prediction? How much power is going to be dissipated as heat? Is it going to be more than 81 watts, the same, or less? Well, if we've got the same resistance, which we do, 900 ohms, but this time the current, 6 amps. That's a huge amount of current. So that travelling through a cable is obviously going to create more heat than if you've just got a small current travelling through the cable. So P is I squared R. This time it's 6 squared multiplied by 900. That's the same as 36 multiplied by 900. 32,400 and power is measured in watts. Are we finished? Nope. Always double check the question, make sure you're not throwing away an extra mark. We've got to give our answer in kilowatts. 32,400 is the same as 32.4 kilowatts, because kilo means 1,000. If you were to take that number and multiply it by 1,000, you'd have the same number as that. You pay for electricity in terms of how much energy you use. Explain what will cost more to run, a 3 kilowatt kettle or a 2 kilowatt hairdryer. Now this is a bit of a trick question. That's my clue. What will cost more to run, a 3 kilowatt kettle or a 2 kilowatt hairdryer? It's a trick question because it depends on, if you pay for electricity in terms of energy, let me just rearrange this equation, that energy equals power times time. You can see that the total amount of energy that you use depends on the power of the object, but not just that, how long it's on for. For example, if you thought, oh well, obviously the 3 kilowatt kettle's going to cost more. Well, if you've got 3,000 or 3 kilowatt, 3,000 watts, and it's on for, I don't know, 10 seconds, then the total energy it's going to use is 30,000 joules. But if you've got the 2 kilowatt hairdryer, so power is 2,000, and that's on for 200 seconds, you know, say you're drying your hair for just over 3 minutes, 200 seconds, well, then we've got 4, 1, 2, 3, 4, 5. We're using 400,000 joules or 400 kilojoules. So even though the kettle uses more energy per second, 3 kilowatts means 3,000 joules per second is being transformed. If it's not on for as long, then it's not going to cost as much. 20. Compare AC and DC in terms of the movement of charges and the voltage. So AC is alternating current, DC is direct current. I want you to describe the difference in the movement of charge. In the case of normal electricity, it's normally electrons, so the movement of the electrons, and also what happens to the voltage of the supply of electricity as well. Okay, so for this we'd want to say that let's just do it bit by bit. So in direct current, the charge moves in one direction. In other words, it's a current that will flow around in one direction. A battery is a good example of direct current. It always moves from, well, the electrons move from the negative side around to the positive side, and they'll always move in that direction. But for AC, the charge, it's called alternating current for a reason. It alternates direction, so the charge moves back and forth. So the electrons kind of move back one way and then forward the other, back, forward, and they kind of vibrate. In terms of the voltage, for DC, like a battery, the voltage remains constant. So you always get, I don't know, if you use a 1.5 volt battery, you're always going to get 1.5 volts from it. The alternating current, the voltage changes from a maximum to a minimum. Mains supply actually goes all the way from 0 volts all the way up to I think it's 320 volts, and then on average it works out at 230 volts, which is what we, that's what we talk about when we talk about the mains electricity. You plug something at the wall, you get 230 volts. That's just an average. Actually, the alternating current is alternating between 0 and 320. So we just need to know that the voltage changes, but for DC it stays the same. The next question. I'd like you to tell me the name of those 3 wires in a plug. We've got a green and yellow, we've got a blue, and we've got a brown. A, B, C. Well, A, the green and yellow one, is known as the earth wire. Remember that because it's got green on it. The majority of the earth's blue, but there is some green on the earth. B, I remember the position of the blue wire because blue starts with BL and the blue wire goes in the bottom left. Bottom left. The brown wire starts with BR, so it goes in the bottom right. I've just given the name of that one. So see, the brown one is the live wire and the blue one is the neutral wire. So I remember the earth because it's got green in it. I remember the brown wire because if you get electrocuted, because it's live, it's a slightly inappropriate way to remember it, but let's just say if you get electrocuted, there's a slight chance that you might brown yourself. Moving on, that only leaves the neutral wire to be blue. So brown, live, bottom right, blue, bottom left, neutral, earth wire at the top, green and yellow. Which wire should there be a fuse attached to? In the plug, what we're missing, there should always be a fuse attached to the live wire before it actually gets to the plug. The fuse must always be attached to the live wire. Explain how a fuse works. Have a go yourself. A fuse is actually just a wire. It's a cylinder that has metal contacts on that end and that end, and in the middle there is a single wire. Now that wire gets hot. When a current passes through it, it gets hot. If too much current passes, it breaks the wire and therefore it breaks the circuit. This is what we mean when we say that the fuse has blown. we mean that the wire has broken. Why do we want this to happen? Well, if there's a sudden surge in current, it could damage our TV or the Xbox or whatever you've got that's connected into the mains. And so by putting a fuse on the plug, it means that if there's a problem with electricity and there's a sudden surge of current, it will heat up the wire will break, and it will mean that the TV or Xbox is now in an incomplete circuit. It won't be on. People may think that if the fuse blows, that's a really bad thing. In fact, if the fuse blows, it means there's a good chance that your expensive device has actually been protected because it's cut off the circuit. It's a bit like throwing a permanent off switch. Then obviously you have to replace the fuse if you want to get the device working again. Explain the job of the earth wire. The earth wire is very important when it comes down to safety. I'd like to see if you can answer this yourself and then check back on the video. Okay, the earth wire will always be connected to the metal parts of a device. So for example, on a hairdryer, usually the body's made out of plastic because plastic's an insulator. But inside the hairdryer there may be metal parts, and those metal parts will be connected to the earth part of the wire that goes to the hairdryer. And the reason for this is that if there is a problem with the device, the earth wire is connected to the metal parts of the device so that the electricity will flow. I'm just going to draw a line down here. It will flow to earth. That's why we call it the earth wire. It's actually a wire that's connected to the device that flows all the way back to earth. Or sometimes what we say is that the device is grounded. So let me just draw a diagram of what that looks like. Let's say we've got a machine and we've got a motor running. We're going to have a brown wire that goes to the machine. We're also going to have a neutral wire which comes from the motor, so the electricity is going this way and that way. Now, if there was a problem and let's say a wire came loose out of the motor and it touched the metal case, this would now mean that electricity could just flow directly onto the case. So along comes me, Mr. Percy. If I was to go and touch that, if there was electricity that could get onto the metal case, it could flow through me and float to the ground, and that would electrocute me. So, to protect me, we have a third wire, the earth. Now this means that if the electricity circuit inside the appliance goes wrong and it connects to the case, the metal case, so this has to be metal. If that happens, then the electricity will flow onto the case, but now, rather than going through my body, which has got quite a high resistance, it'll just flow back down the earth wire in a way. So the earth wire provides a path to let electricity go down to the ground without going through your body. Last question. Give two advantages of a circuit breaker compared to a fuse. So a circuit breaker is an electronic device which switches off a circuit when it detects a change in the current. So if the current is too high on one side of the, if the current is too high here compared to there, the circuit breaker will go, oh wait a minute, there's been a sudden rush of electricity here, it's high, so what I'm going to do is I'm going to cut off the circuit. So the circuit breaker would be back, you know, in the house, in the main part of the house, and if it detects a sudden surge in electricity, it would actually cut the circuit off. The similarities are that they are both safety devices, and they both cut the current if there's a problem. The advantage of a circuit breaker is that the circuit breaker is faster. Because it's electronic, it can detect a problem straight away and cut the cut the switch immediately. A fuse has to get hot, and it takes time, not long, but it just takes that split second longer where the wire has to heat up and break. Now in that time, current's still flowing, and if you're unlucky, it could cause damage to your device. Another advantage is that you don't have to replace a circuit breaker. If it flicks off, you can actually just check your device. You know, maybe there's a problem with the device that you're using, so you get rid of that, and you would just reset the switch. You don't have to replace anything with a circuit breaker. With a fuse, if you blow the fuse, you've got to actually go out and buy a new fuse, so that's a disadvantage as well. Okay, in the next video, CP10, magnetism and the motor effect, and then the last video after that will be about particles and energy. So, hope to see you there.